All right. Hi. Thanks for that introduction. Um, like I said, I'm here today to talk about building an Arduino that can cover a PlayStation memory card. And this little flailing nugget on the right is my son, who will be 3 weeks old this weekend. Um, and he is now why I am so tired all of the time. Um, and maybe it's part about being a new parent, but I've been thinking about the past a lot lately, specifically 1998, where few experiences meant more to me at the time than when I saved the planet from Sephiroth in Final Fantasy VII, an epic RPG for the original PlayStation console and probably one of my favorite games of all time. And I recently found this, my original PlayStation memory card, hidden in a shoebox during a move. This little rectangle of flash storage holds my Final Fantasy VII save, and 22 years ago, it was probably the most precious thing I had ever owned. And so I figured, hey, as a new father and as a lover of cats, it would be nice to have at least one thing in my life that I feel I could tell what to do. So I decided I wanted to extract my Final Fantasy VII save to a computer so I could load it up in an emulator. And to do this, I'd use an Arduino as a middleman. And if you're not familiar with the Arduino, don't worry. It's a very handy board to jumpstart electronics projects. And it has a USB serial port that we can use to send data to a PC. But first, I needed to start with the memory card itself. What was its format? How was it put together? And so standing on the shoulder of giants, I looked at some reverse engineering documentation and realized that I was going to have to learn binary. And my knowledge of binary at the start of this project was something that was basically a 0 or a 1. And that's true, and we call that a bit, and it's pretty much the core building block of computing. And we also count our bits in binary. So with regular numbers, decimal numbers, we count from 0 to 9, and when we run out of digits, we add 1 to a column on the left, and we go back to 0 and start all over again. When we get to 99, we start a new column and go to 100, and each new column is raised to a power of 10. And the exact same rules of counting apply to binary and also to hexadecimal. But the crucial difference is we raise our columns to a power of 2 and 16 respectively. And another neat thing about hex is that a 2-digit hex number is 4 bits, meaning we can represent a whole byte with just 2 numbers. And because if we smush 8 bits together, we get a byte, which is a really integral unit of digital information, and it gives us a total representation of 256 numerical values in binary. And we can actually assign additional meaning to those numbers. So for instance, there's ASCII, which is a standard for encoding text and symbols with numbers. So in ASCII, the decimal number 67 represents a capital C. And manipulating these bits and bytes to add our own meaning is really how we build up all of the digital media we interact with, from reading a PDF to streaming Never Have I Ever on Netflix, or busting out Cloud's awesome Omni/Limit Break in Final Fantasy VII. And so PlayStation developers could store their ones and zeros, but they were limited by the constraint of frames and blocks, and basically size. So a frame is 128 bytes. And this is actually the very first frame on any PlayStation memory card represented in hex. And it basically does nothing but spell out MC. And now if you take 64 of these frames, you get a block of 8,192 bytes. This is a representation of frames on a standard 1-block PlayStation memory card save. You get 1 frame for title information, 3 for a nice little icon, and the remaining 60 can be used by the game to store saved data. And the memory card holds 16 blocks. It gives 15 to the user, and it keeps 1 for itself as a directory listing. And so 16 blocks gives us 1,024 frames. And the nice thing about this project is that we don't have to worry about how the frames are actually really laid out. We just need to know that they exist. We need to move all of them from one location to the other. And with that, I felt like I understood the shape of the memory card. And so the next step was to use the Arduino to communicate directly with it. And the idea was to fool the memory card into thinking the Arduino is just a regular old PlayStation. The key here is these magical little digital pins that run up both sides of the board and their ability to create an electrical circuit with the memory card. Luckily, the PlayStation memory card mostly conforms to a very established protocol for doing this called SBI, which is common enough to have its own Arduino library. And as a web developer, I know a thing or two about using external dependencies, so I felt very comfortable here. And these actually correspond to the pins on the memory card itself. If we connect these pins to the Arduino pins, we can create a circuit and start communicating. And the PlayStation memory card can send the information electronically down its data wire by turning its voltage on or off. When we send voltage through the connection, we say it's high, and we interpret that as a 1. And conversely, when we don't, it's low, and we read that as a 0. And this is another reason why binary is so important. We reduce all of that information back down to its most basic part. We send it as a million ones and zeros, piece by piece, through an electrical signal, and then we can rebuild it on the other end. And we can also use another wire to create a clock signal between the Arduino and the memory card, which aligns the devices so that they can only read the values when that clock is high. This helps our communication and our data stay reliable. And what you can do is you can actually solder some wires directly to the memory card pins and then plug that into the Arduino ports. Now, I have never soldered in my life, and it's hard and it feels super dangerous. And fun fact, this card here is actually my brother's because I didn't want to risk my own card first, and I have not told him I've done this. And if you're looking for a less permanent solution, you can do this. You can yank out the whole memory card reader from an old broken PlayStation and solder wires directly to that. And when you do either of those things, you'll be able to make this connection. And then the PlayStation memory card is now set to let you read data on a frame-by-frame basis. And to do that, you basically need to follow the playbook on the left in that exact order. The Arduino issues the send commands in green and receives the data in orange. SBI always sends and receives a byte, so a lot of our outgoing commands are just empty bytes set to 0. And to initiate the communication, we have to program the Arduino, which uses C++. Don't worry if you don't know any of that. I only knew enough to hack together this read frame function, which takes an argument for the address of which frame to read. But our address that we send in is a 16-bit number, so we have to break it into two 8-bit bytes. Because there are 1024 frames in total, we can't hold a number that big in a single byte. So we have to send it to the memory card as 2 separate bytes. And then we can tell our attention wire, another one of our wires, to go low, which is kind of the bat signal to the memory card that we're about to be sending some commands. And then we can begin that SBI transaction. Thanks again, SBI library. And I've extracted a command function here, which handles the sending and receiving of the bytes. We're not using any of the return bytes for the first 10 commands, but we still need to go through those motions. And now we get to the meaty bit. And at this stage, the memory card goes byte by byte through the requested frame, and the Arduino outputs its information through its USB serial connection. And we also send across the results of the checksum and the confirmation byte. And we finish this off by wrapping up the SBI transaction. We set the attention wire back to high, so we can signal that we have no more commands for now. And now we can finally switch over to the PC to make some sense of all of this. I'm using Python here, but any scripting language that can write binary files or access serial ports will be fine. So we're on the PC, and we're reading what the Arduino writes over that USB serial connection by wrapping another library, PySerial, into a memory card class, creating a read frame method, and assigning that data, checksum, and status bytes we transmitted from the Arduino to variables in our Python script. We validate that the status is correct, and then we return the data. Over in our main block, we read the command line arguments and we instantiate the class. And we know how many frames there are, so we can just open a binary file, create a loop, and run the read frame method until we've transferred all of the frames into it. I know, all of that work, and you've come to this awesome tech conference, and basically my grand conclusion is the bog standard loop. I'm sorry about that. And the real question, of course, is, did it actually work? And this would be a super depressing talk if it didn't, I suppose. So I'm going to try a little bit of screen sharing right now. Hopefully that's working. That's live. That is an emulator. That is a PlayStation emulator running right now. This is Final Fantasy VII. I can click continue. I can choose my memory card slot. It loads a bit. These are my original memory cards showing up in a PlayStation emulator. We can choose one of them and it can load. It'll take a little while. It's an old console. But just thinking about this makes me feel 22 years younger. And it's kind of amazing the memories and feelings I attach to these files. I mean, that is a golden chocobo right there. I have stories about my life around so many of these games, and maybe you've got some weird old storage device lying around somewhere that might be worth a trip down memory lane. I would love to hear about that. And also, I would just like quickly finish by shouting out to our wonderful conference organizers and to all the key workers who've kept us fed, healthy, and supplied over the past couple of months. All of those people are heroes, and thank you very much.